on the fifth day of his STTP, and in the third session, uh, we have Dr. Rajat Saxena as an expert speaker of today's session. He holds BTech and MTech and PhD in energy engineering. Dr. Saxena completed his bachelor's degree in mechanical engineering from UP Technical University and did his master's and PhD from Indian Institute of Technology, Delhi. Presently, he is working as assistant professor in Department of Chemical Engineering, School of Technology at PDEU. His principal research interest lies in the field of thermal energy storage for various applications and applications of thermal energy storage by using a conventional method of increasing thermal mass of buildings using fast chain materials, that is PCM, and has been explored meticulously during his research work. He is currently working on developing systems that can utilize fossil fuel and move towards greener tomorrow. He has published a number of international journal papers, book chapters, and attended several international and national conferences. His area of interest is particularly from design and development of thermal energy storage systems, building energy conservation, heat transfer enhancement using nanofluids, solar thermal applications, and alternate fuels. He has on his credits various achievements. One of those is he has got the Best Paper Presentation Award in Conference on New Frontiers in Energy and Environmental Sustainability, NEFES 2021 at PDEU Gandhinagar in February 2021. He has received early doc fellowship at IIT Delhi, New Delhi, as a post PhD. He won first prize in Industry Day 2019 for Make in India theme at IIT Delhi in September 2019, and he has won the Best Paper Award on at 4th World Congress in International Conference on Heat Transfer and Fluid Flow, Madrid, Spain in August 2018, and he has won the Run-Out Prize at International Conference NFEST 2018 at Delhi Technical University in January 2018. So we have such a luminous personality today we have with us, and he is going to present the today's presentations on fast chain material utilizing fast chain material utilizations for energy conservations and environment management applications. So I would request Dr. Saxena sir to please start this session.
Thank you so much, sir, for introducing me. And I'm really overwhelmed. Sir, can you please help me if my presentation is visible? Is it?
No, sir.
No, sir. Please share your slides.
Is it visible?
Yes, sir. Yes.
Perfect. So, very good evening to everyone. In fact, good afternoon to everyone. So I will be presenting on the topic phase change material utilization for energy conservation and environment management. Energy conservation and environment management is very close to my heart, being my MTech, and phase change materials is again very close to my heart, being my PhD. So today I'll try to amalgamate both of them, and since it is highly relevant to the theme, since we are doing an FTP on this same topic, energy conservation and environment management, so I think this topic would be highly relevant for all the listeners who are attending this FTP today. So the theme, the overview of what I'll be speaking on is the introduction to the topic, then phase change materials, what are phase change materials, the physics behind, then classification of research domains in the field of phase change materials. Then I'll be also talking about applications, basically case studies, which are related to environment management, energy conservation, and of course to provide thermal comfort. So this is just a gist of what I will be covering in today's session, and I hope you'll be patient enough and you'll not be bored with what I'm speaking. And I also will try to ask questions. It will be good if I get a response, because then it will be a two-way conversation, and I hope I'll not make you sleep over here. Okay, so I hope I'll get a response. Yes? I hope yes. To start with, as I am sure already energy has been discussed, might have been discussed already. What are different methods of energy generation? In fact, most of you may already be aware about it, right? We get energy either from natural gas or from coal, from nuclear power, and the what you call the latest trend, and most of the research is being concentrated upon the renewable energy. But do you have any idea how much amount of if you talk about global perspective, how much amount of renewable energy do we get of the total amount of power we actually utilize? Any ideas to anyone? Any idea? Okay, so it's good that there will be something which I'll be delivering, and people will be gaining from today's lecture. First, I would like to tell India is the third largest energy consumer in the world, right? In the table, it might be shown on the fourth number, but India stands third after China and US. Russia utilizes 5.2% of the total global energy consumption, whereas India consumes 5.8, that is more than Russia, right? The question which I posed was, do you really feel India is doing bad in terms of energy generation? Because you might be listening that global news always pinpoints India and China utilizing non-renewable sources and doing for development, because India is a developing nation and we utilize a lot of energy. And it has been said that India is utilizing a lot of resources, causing a lot of pollution. But friends, don't get like boggled by what media says. In actual, I would like to give you some numbers. If you talk about entire world, the renewable energy, it's only 4%. If you talk about global average, right? They get their power from renewable energy by only 4%, and India gets, anyone any idea how much do we get our renewable energy? What is the percentage of renewable energy of the total energy share we utilize? Anyone? It's roughly around one fourth of our energy. That is 25% of our energy we utilize is coming from renewable energy, right? So this is something which I wanted to tell, since many people may not be aware about this, not working in the field of energy. But of course, this session is related to energy conservation, and the significance of energy conservation must be very much understood. So with this, as we all know that India is a coal-based economy. Why it is said so? Because 70% of our energy comes from thermal route, of which 80% of the thermal route energy comes from coal, right? So in aggregate, we may say around 58 to 59% of our total energy which we are using at our home is coming from coal, right? So even if you feel that you are not polluting the world, right? Maybe you might be having a very good like you might be using cycle, you may not be using vehicles, but still, if you are using electricity, that means you are generating a lot of pollution, right? And of course, we can't do, as of now we cannot do anything, but still I would tell you certain suggestions, okay, how to incorporate and how can we contribute in the growth of our nation, right? Because soon we'll be leading to energy crisis, okay, and I'll come to it in just next slide, as you'll see, because as you all know that we are generating like around 60% of our power from.
Sir, can I interrupt, sir, for a second?
Yes,
Sir,
yes.
are you on the first slide, sir? The
No, no,
introduction
no,
slide?
no, I am on the
Okay,
fourth.
because we are not able to see the slideshow.
Oh, just,
So
just.
I request you to stop presenting, and then select your entire screen to present, and then go on the
Okay.
slideshow. Yes, sir.
Perfect, perfect. I'll do that. Just a
Okay.
second. I hope my screen is visible now.
Yes, sir. Your screen is visible, and can you? Yeah,
It is changing.
Now, yes, yes. Now we are on the overview slide.
Perfect.
Yes, sir.
So I have already discussed this. Okay, and so this was what I was talking about. India stands third when you talk about the amount of energy consumption, and 4% of the total. What you call when you talk about world's perspective, the world is using only 4%, generating only 4% of power from renewable energy, whereas India gets around 1/4 of its power from renewable energy. So next time anyone says that India is not developing, please reply this with the answer. Again, I would like to say we still use a lot of coal. Agreed. Around 70% of our power comes from thermal route, of which 83% comes from coal, which means around roughly around 58 to 59% of our power comes from coal. So please, it is high time now that we should think that it's not just us. You. Right? So we must think of alternate resources to generate power because the energy demand is rising, right? But we have to move towards sustainable future, right? Now, sustainable future can be of two ways. First one is if we change or transform the energy which is being generated through non-renewable sources, if we get it through renewable sources, that is one way. Perfect, right? And but along with this, right, I would still say will lead to crisis. Why? Because it is very very important that if you keep generating and you keep utilizing, right, without any check, then of course there will never be a limit, right? So there has to be one more measure that has to come into picture, that is energy conservation and energy efficiency, right? So it has become a necessity today because energy demand is going to rise, of course, because energy is being generated mostly from non-renewable sources. The global climate also will be impacted because of that. Then there will be constraint to energy supply, right? Because you will be only a limited amount of energy can be generated because it will have environmental constraints, right? So we will have to shift towards sustainable development, and sustainable development does not say you generate more and more, right? It says you generate as much it is required, and that requirement has to be set, right? We need to use the available energy more judiciously. That is the need of the hour because there is energy crisis which is going to come, right? We need energy conservation to protect the environment, to save the cost of living, and of course we have limited sources because still we are dependent heavily on the what you call the resources like oil and coal, right? And we have limited supply of that. Then to ensure energy supply to our future generations, that is what sustainable development is all about. But our topic again, I would like to emphasize energy conservation and energy efficiency needs to be the motto for every individual. Now I will tell you that most of the people think this energy conservation and energy efficiency is one and the same thing, right? Do we can anyone in the audience tell me what is the difference between energy conservation and energy efficiency? Most of the people use it interchangeably, right? But anyone who can answer, just a simple question. Energy conservation, or I'm not asking you as a question, I'm just asking your comments. Energy conservation and energy efficiency, are they same thing or are they different? Audience, anyone? Faculties. uh, okay, then I'll only answer. See, generally, what happens is people generally take energy efficiency and energy conservation as one and the same thing, but actually, it is not. Right? Energy conservation is achieved when growth of energy consumption is reduced in physical terms. Okay. I would say energy efficiency is just part of energy conservation, right? How will I explain it? I'm going to explain it with one very simple example. Say, for example, I'm sitting in a house, right? It's a bright summer time, right? And I'm feeling cold in my house because my AC is turned on to 21 degrees centigrade. I'm quite comfortable. In fact, I'm not comfortable. I'm feeling a little cold. So, general perception is now it comes with the psyche of the people. What they will do is either what I can do is either I can put on a pullover over me, right? I can put a quilt over myself to be comfortable. Second option is I can switch off my AC, right? If I'm switching off my AC, I am reducing the energy consumption in physical terms, right? This is known as energy consumption directly, right? So if I'm switching off my AC, or second option is if I'm running my AC at 21 degrees centigrade, I'm feeling cold. What I can do is I can run my AC at 27 degrees centigrade, right? 27 or 26. I can increase the temperature, right? That is also energy conservation, right? And anyone has any idea how much amount of energy can be saved just by increasing 1 degree centigrade on your temperature scale of your AC? Any idea? As per GE, Vice President of GE, I attended one of his lectures. He told 3% of power can be saved, right? Just by increasing 1 degree centigrade of your air conditioner, you can save 3% of your power. So now you can imagine. Now the question comes, then why 21 degrees or 22 degrees? You might have heard that word of thermal comfort, right? Thermal comfort, where people might already say that we should run our AC on 22 or 23. Okay, those were the rules which were made by people living in European countries, or in US, right? So they have set the limit based on their temperature conditions. The point is the temperature over there is say 10 degrees centigrade or 15 odd degrees centigrade, right? Now they have to heat their room to come to the comfort temperature, right? So based on their understanding, they have given the comfort temperature at 21 degrees centigrade or 22 degrees centigrade for females and 23 for males. Okay, if you might there, of course, then there is a window which comes when you talk about RH factor also. I'm not going into that details, but again, the temperature of 27, if 50% RH is there, the temperature of 22 degrees, 23 degrees is comfortable, right? They have set it to 21, 22, 23 because they are heating their room from 15 degrees or 10 degrees to 21 degrees or 22 degrees, right? But in our scenario, if you see that window is between 22 to 25 degrees centigrade, right? The comfort temperature is between 22 to 25. It can be even 26 and 27. It depends on the person and individual, right? So now we Indians, what we do, since we have studied from books of European countries, so what we do is, yes, the comfort temperature is 22 degrees centigrade. So since we are sitting at 45 degrees centigrade or 40 degrees centigrade in summer, we are cooling our room to 21 degrees centigrade, right? But actually that was because of the heating. That temperature was set because of the heating. We could easily be comfortable at 25 degrees centigrade and 27 degrees centigrade, right? So if we do that, we will be able to save how much amount of energy? I've already told you, 1 degree means 3% of power, right? So if you are increasing the temperature of your AC just by 5 degrees centigrade, you will be able to save around 15% of power. Just give me a second. So you will be able to save around 15% of power, and this is again amazing, right? You don't have to do anything. You just have to set the temperature of your AC at the correct temperature, right? Don't do it 18 degrees centigrade because it is done in England. Don't do it at 20 degrees centigrade because it is done in Europe, right? Do it 26 or 27. Your electricity bill will be reduced by 10% straight away, So this is one thing, one application based on energy conservation. Now I was talking about energy efficiency. Now how is energy efficiency different? I'll tell you. See, I had an AC and I switched it on and off. That was energy conservation, right? Second option was increasing the temperature. That is also energy conservation. Third one is, if instead of having a 3-star AC or 2-star AC, since my AC is old, it is a 2-star AC, right? If I in place say a 4-star or 5-star AC, right, the same comfort will be achieved at lower energy consumption, right? This is referred to as energy efficiency. So I hope difference is very clear, right? If you implement energy efficient operations, of course it will lead to energy conservation, but all energy conservation operations need not be related to energy efficiency. Clear? If you talk about energy efficiency, it is achieved for specific product or process, right? Now since energy conservation is a wider topic, so we must understand there is a difference between energy efficiency and energy conservation. Energy conservation is reduction of energy units, right, based on psyche, based on, of course, also on the product or equipment which we are utilizing, and energy efficiency is related to the equipment. Of course, energy efficient operation example is, we changed from incandescent bulb to LED bulbs, right? We changed from 60 watt power to 8 watt powers, right? Do you know how much global impact did we how much environmental impact does this have? A CO2 emission of 48.4 grams per hour is produced by 60 watt incandescent bulb, whereas for LED of 8 watt, it produces only 6.4 grams per hour of CO2. So you can imagine, right? I'm just giving you, see, number is clear, 60 and 8, right? But its environmental impact I'm just trying to show in form of grams, right? Now you can imagine if this is one refrigerator or one AC, right? A 1 kilowatt AC, how much energy it will produce, how much CO2 it will produce. So that can be also calculated, right? So this is just a comparison between energy conservation and energy efficiency. Difference between the two, I hope it is clear. And with implementation of energy efficiency, like now instead of incandescent bulb, we incorporate LEDs in our houses, and you see it is leading to energy conservation, which is easily visible in our electricity bills, which are now relatively lower. Now talking about this is my last slide on introduction, and this is one of the very important slides which I feel just to make you feel the importance of energy conservation, right? So talking about energy conservation, we say that what will happen if we just switch off our light, right? This is general perception. People might, even students, you can talk to this to your students as well. I gave it this example to my MTech students also. Like we think like what will happen if we just close one fan? It's just one fan, right? So I'll just tell you the per capita energy consumption of India, right? It was 1149. I hope my pen is also visible, right? 1149, right? Is my cursor visible? I hope it is. Yes, right? So 1149 is the energy consumption of say 218, right? 2018. In 2019, the per capita energy consumption was increased to 1181. Now this number looks very small, right? Only an increase of say 32 units, right? 32 units, but per person. You know what is the population of our country? It's 1.4 billion, right? And with 11% or with 15% of wastage, for every unit of power consumed, right, we have to generate around 1.7 billion unit of electricity. Now you can imagine, right? 1.7 billion unit of electricity just for saving 1 unit of electricity. If everyone, see, if everyone in India saves only 1 unit of power, right? Saves only 1 unit of power at home, right? In an entire year. Not, I'm not talking about one day, right? If you save only 1 unit of power in entire year, you will be able, and everyone in India does that, we will be able to save around 1.7 billion unit of power that is generated at the generation level. So this is just a power of energy conservation, right? So this is basically why the courses like these needs to be more preached amongst the students, among the faculties. First, faculties must be made aware about all these things, right? The impact is huge, right? So that has to be understood. Now this was about energy conservation. Why energy conservation, right? What is the impact, what can be the probable impact of energy conservation? Now talking about that, I would also like to tell, it's very easy to tell about stories, but then how to implement it is another task, right? So one of the implementation method is utilization of waste change materials, right? So what are these phase change materials? Any idea, anyone? Anyone? Anyone in the audience? I will be very happy if someone replies.
So phase change material means is a type of material that get its phase change with relation to its temperature and pressure condition.
Very good, sir. Actually, I would like to tell in a very simple way, right? Water is a phase change material at 0 degrees centigrade and 100 degrees centigrade at atmospheric pressure,
It's a water.
right? Matlab, it's just in plain language so that everyone can understand, right? Water is a phase change material at 0 degrees centigrade and at 100 degrees centigrade at normal atmospheric pressure, right? It melts from solid to liquid at 0 and liquid to gas at 100 degrees centigrade. So any material is changing its phase, right? So that solid, liquid and gas, these are the three phases, and the interchanging between those phases, right? That is what is here referred to as phase changing materials, right? So whenever you're doing an operation, during that operation the temperature is such that the material is undergoing its phase change. That phase change can be from solid to liquid, or it can be from liquid to gas. Now, which is my matter of concern, that I'll tell you. I'll be talking more on solid to liquid, and why I'll be talking why solid liquid phase transitions have been studied more. That also reason is simple. The volume change is quite less when it compared to solid as compared to liquid gas transitions. You very well know ki, if we are melting a water, if you are melting ice, right, it will turn into water. The volume is very less. The change in volume is very less. At the same time, if that same amount of water is being evaporated and it is converted into steam, the volume required will be very higher, much higher, right? So that is the difference. So it is difficult to handle that change in temperature in different applications, change in volume for different applications. So that is why we prefer going for applications for solid liquid transformations. But of course, from liquid to gaseous transformations are also very much important. Of course, we are getting most of our power from that, right? Because we produce steam, and that steam is only utilized for generating power. But of course, not for generating power. We are talking about energy conservation. So I'll be talking about it, how this phase changing option is applicable and helpful. So why we want to go for phase changing operation? So one of the most important which I speak to my students most of the time is, see, what happens is when a phase changing material is absorbing heat, right? As I've told you, you all know that water is a phase changing liquid. It changes its phase from solid to liquid at 0 degrees centigrade. And when it is transforming, the temperature does not change, right? But a large amount of heat, say for example, it is changing from solid to liquid, a large amount of heat is absorbed, right? That is why the nearby area is getting cooler. Yes, you may not feel it here, but maybe not in Gujarat. But if you're living in a hilly areas and there has been a snowfall, the day on which snowfall is taking place, it is not the coldest day. The coldest day come when the snow actually starts melting. What happened is when snow melts, it takes the environmental heat, and actually the environment starts feeling colder when the actual melting of this snowfall starts, right? So this is one of the reasons, right? So they absorb heat at constant temperature. If they are changing, of course, they are changing from solid to liquid. If they are changing from liquid to solid, they will be releasing energy, right? The same amount of energy is being released, and the nearby people will feel hotter, right? So this is something which is being utilized. That is the amount. See, in general, whenever you're heating a water, right, we'll give heat to water. What will happen? The temperature of water will increase, right? During the phase change, the advantage is when you add heat or remove heat, right? Because it is undergoing phase change, the temperature is not going to change. So we can target such applications where we want to keep temperature constant, right? So all those type of applications, some of those applications I will be discussing today. Now another very important characteristic feature about these phase change material is that it is important that it should not degrade with time, right? You talk of water, it has already undergone billions of cycle, right, of melting, solidifying, then melting and solidifying, but still we get water as it is, right? And it has happened billions of times, right? Even when we were not here on this planet earth, water was there, right? So water is quite stable. But what about other materials? They are not like same, they are not stable as water is, right? So they tend to break down, right? So actually it is important that the stability of these materials should also be in the required range, right? It should be at least it should be able to bear 1,000 cycles or 2,000 cycles. So research is still searching such materials which can undergo phase transformation, of course, plus they do not degrade with again by doing it again and again. So that is also very important, right? Why latent heat storage? Of course, the amount of energy stored by latent heat can be 50 times higher than stored in the sensible heat. Okay, so this is just number I'm telling you. If you talk about sensible heat, because say for 5 degrees centigrade, here I have shown for calculation for 15 degrees centigrade. If you show it for 5 degrees centigrade, you will find it can be as high as 50 times the energy stored for sensible heat storage materials than the phase changing materials. The process is simple, as I've already discussed in my words. If it is a solid, right, when you heat it, it will gain heat, the temperature is going to increase, but then there will be a point which is known as melting point of that solid, right? What will happen? It will absorb the heat, but the temperature is going to be constant, right? During this phase, during this time, it is going to change its phase from solid to liquid. Similarly, it will take more heat and it will change from it will again start the temperature of the liquid will start increasing up till its melting point. And when the melting point will come, when the when the boiling point will come, it will evaporate and it will convert it from liquid to solid phase. So this is how the physics behind how PCMs work. Now, types of PCM. So it is of three types: sensible, latent, and chemical energy storage. So sensible heat storage is, as I have already told you, the material who is not changing its phase, solid phase, it is there. So it is a sensible heat storage. Example, a rock bed, right? A lot of heat is being stored in rocks, right? And this kind of practice, it is not common in India, but in Canada initially they started with not just started, they're still using this sensible heat approach, right, to store energy of during the summer season and utilizing it during the winter season, because their winters are long, right? So what they do is they put this hot water during the summer inside the earth, right, where rock bed is present, right, and it will stay there. And when it is cold winters, so they'll take out that water which will be hot, and then that is used for district heating, right? Then there is latent heat storage systems. As I've already told you, latent heat means storage of heat in form of this phase transitions. Like I want to store heat in say in water, right? So I'll give some heat to water. What will happen? Water first it will change to 100 degrees centigrade, and then what will happen? It will evaporate and it will convert into steam, right? Whenever I require heat, I will take heat from the steam and it will convert back to water, right? That's it. Now steam is also at 100 degrees centigrade, water is also at 100 degrees centigrade. Temperature hasn't changed, only thing is the heat which we have given. And this of course this latent heat involved is way higher than compared to the sensible heat involved, as in the case of sensible heat materials. Chemical energy storage, what happens is there are two materials reacting at a particular temperature, they react and they give out heat, right? And these kind of reactions should be reversible. So there are many people who are working on this. This is, and again, many chemical engineers are working on these kind of reactions, which are reversible also and can store large amount of heat and can give or take, depending, right, whether the equation has to move in the forward direction or in the backward direction. If you talk about latent heat storage, it is gas liquid, solid gas, and solid, right? Then for solid liquid transformation, as I've already told you, I'll be concentrating more on solid liquid transformation because the volume change is quite less. Of course, then you talk about it is of two types. It can be organic and inorganic in nature. Organic means eutactic, means melting in the same temperature. Two materials mixed in such proportions that they are melting together at the same temperature, right? That is known as eutactic. So organic eutactic is also there and inorganic eutactics are also there. Then comes paraffins. Paraffins is simply like waxes, wax you might have heard, right? Mob. Then fatty acids, right? Fatty acids also you might be well aware of, like coconut oil, right? In fact, there are other oils also then that can be used, right? So these are all fatty acids basically. Talking about inorganics, then inorganics it's like eutactics again. That is mixture of two or more salts or single salt alone with water, that is hydrated salts. So these are different classification of thermal energy storage systems materials. Talking about comparison between inorganic and organic, so which material we should go for, that is very important, right? Since I am going to discuss about different case studies also, so it is very important which PCM is to be selected, right? So two things. First of all, first and most important thing is cost, right? So inorganic PCMs are very cheap compared to organic PCMs, right? Next comes the thermal conductivity. Thermal conductivity, of course, of both the types of PCM is less, right? But inorganic PCM has relatively better thermal conductivity than organic PCMs. Now, then again, one more thing: storage capacity also for inorganic PCM is higher as compared to organic PCMs. Generally, it has been seen, right? But then you will say, then why are we actually studying organic PCMs? The reason why do we actually study organic PCMs is the stability of organic PCMs is quite high, right? The cyclability is very high, right? In fact, I have worked on PCMs which have what you call cyclic stability of over 2000. Whereas in organic PCMs, it is difficult to get stability of even 200 cycles, right? So that is one of the limitations of using inorganic PCM. Another important thing is there is subcooling effect which exists in case of inorganic PCMs. What is subcooling effect? Probably when I'll be coming up with in the later on slides, I will be explaining you with the help of diagram, right? They actually segregate, right, because of the cycling and what do you call subcooling effect. What happens is when it is cooled down, right, it will not actually solidify at its melting point. Say for example, a material is melting at say 30 degrees centigrade, right? When I'm cooling it, it will not solidify at 30 degrees centigrade, it will solidify at 20 degrees centigrade. This happens this is quite common with inorganic PCMs, right? So this kind of effect is known as subcooling effect. Okay, so of course, and one more thing is these inorganic PCMs are basically salts. They are more corrosive. Organic PCMs are relatively less corrosive, only except for what you call organic acids, right? Apart from that, other organic materials are less chemically they are chemically inert and non-corrosive. So now, since most of the people over here are faculties, so I would like to tell it is very important that whichever material we are using, we need to characterize it first, right? So basic properties like specific heat, latent heat, phase change material, phase change temperature, subcooling effect, thermal conductivity. These are some of the properties which needs to be determined well in advance before you actually carry out your experiments. So like some of my students are even working on how to develop these different I've already told you eutactic materials, right? Two materials mixed together in such a way that their melting point is common, right? And generally it has been seen that the two materials which are mixed, they might be having a altogether a different melting temperature. However, when they are mixed together in a particular proportion, their melting point changes to a different degree centigrade. So this is also one of the interesting interesting topics which some of the students are working, right? So since they are developing new phase change materials, so it is important to actually characterize them, right? To get the specific heat, latent heat, phase change temperature, subcooling effect, we can use differential scanning calorimeter, right? There are several manufacturers available in the market. You can take it from Mettler Toledo or Shimadzu or Perkin-Elmer, Marwan, Nesh, TA Instruments, Hitachi. I have worked on both TA and Hitachi, but all of them I have heard they are good and fairly accurate. Of course, with cost comes the accuracy, and then comes the other one property which is generally not given by any of these currently instruments. I'm not sure about Shimadzu, but Shimadzu Shayad gives also the thermal conductivity, but I'm not sure. But thermal conductivity specifically, you have to buy another instrument for measuring the thermal conductivity using thermal conductivity analyzer. Of course, you can build your own experimental setups to measure the thermal conductivity. So that is also option is there. But then since when we write papers, we need to have some instruments, or it's good to show that we have done it from a reputed place. So you can use a thermal conductivity analyzer to analyze the thermal conductivity. Of course, this is also available from different C-therm is one of the good ones. Then hot disk, and there are many others. So that you can find it out. So there are two basically research domains. One research domain lies in developing of what you call phase change materials. The second domain lies in the application of phase change materials. We call energy as an interdisciplinary branch, and here you can see the interdisciplinariness. The left side is totally related to chemical engineering, where materials are being manufactured, then they are being tested, thermal physical properties are being tested using DSE, TGA, DTA, right? Then their short-term, long-term behavior is being tested, right? Thermal behavior, thermal cycling test is being tested. So this is all a chemical side. The second is mechanical side of it, that is development of heat exchangers which are using these phase change materials. right? Analyzing them, creating models, laboratory models, pilot plants, where actual implementation of these phase change materials is taking place, and the applications can be tested. So these are the two aspects of research domains being actually actively going on in the field of phase change materials. So one of the application, now I'll be talking on the applications, right? So there are many applications of these phase change materials. Simple ones you might be very much aware of, like cooling pads, right? Cooling pads are being used these days, very common, right? You have a what you call sprained muscle, you use a cooling pad which is available in the market, 40 rupees, 50 rupees cost, right? You might be also using it before, right? If you're not using that cooling pad, you might be using ice, right? Ice is also a phase change material at 0 degree centigrade. You're using it to rub it over the area which is being sprained, and slowly and slowly the pain goes away. So you have been using phase change materials, right? Now, but when you talk about bigger perspective, so when you talk of renewable energy, right? One of the major drawbacks of renewable energy is that it is intermittent. Intermittent means it is only available during the daytime. If you talk about solar energy, right? If you talk about wind, it is even more intermittent, right? At least we know sun is going to come during the daytime if there are no clouds, right? And we are sure that sun is not going to be available during the night time. But about winds, we cannot be very sure. It may be present right now, it may not be present after an hour, right? So the surety, right, the reliability of renewable sources is still questionable. Of course, this is not the case when you talk of OTEC, right? When you talk of, say, I would say wave energy is relatively better, but still, right, you cannot be very sure about the intensity of wave it is coming. Then you cannot be sure about solar radiation. Solar radiation, we are sure that it is available only during the day but not during the night. So to fill this gap, right, you need to have some storage, or you will only implement renewable energy during the daytime if you are working on solar. Then what about the night time, right? So unless and until you have a storage, this intermittency cannot be held. There has to be some solution to this intermittency, and the only solution is the implementation of storage. So now, what kind of storages can be implemented? These phase change materials are currently being utilized, right? They are working as both heat transfer fluid as well as the storage medium, right? So liquid, these phase change materials, one project is like in solar 2 project at Sandia. In this, liquid is being utilized. In fact, it is not a phase change material, I would call it as sensible heat storage material, right? Because it is going to be liquid, right, throughout, right? So it is more of a sensible storage. But in the second one, as you can see, commercial tower system plant in Gemma solar plant, in this 15 hours of storage is being provided, and in this phase change materials of concept is also applied for storage of electricity, for storage of heat of sun, right? And one more thing I want to add, like storing heat is more energy efficient than storing any other form. Like people might be thinking that nowadays we store energy in batteries, right? Absolutely fine. See, no storage is energy efficient. If you are putting in a storage, that means you are making a overall system inefficient, because some part of energy will be utilized in charging the system and during the discharge of the system. I hope everyone agrees to it, right? Now some part of energy is being utilized. Now the problem is, if you are storing heat, right? So you are storing heat, and that heat will be used to convert electricity, right? So suppose if you have lost, say for example, 30% of heat, so you are losing only 30% of heat. 70% can be still utilized to generate electricity, right? But when you have generated electricity and you are storing electricity, and you have say for example you have lost 30% of electricity, then you have directly lost 30% of electricity. There is no form of generation. Whereas 30% of heat loss means the electricity generation loss would be only 10, because actually only 30% of energy heat is converted into what you call electricity, right? So overall, it is always win-win situation if you go with heat storage than to go with electrical storage. But of course, electrical storage is also necessary at its point, because we cannot put in thermal energy storage everywhere, right? So of course, batteries are required. So that is another means discussion which can be carried out in some other FTP, right? So second application. So this was one of the application of storage, utilization of phase change materials for power applications. The second one is energy conservation through thermal management, right? Many places, if you maintain the temperature, that is also resulting in significant of amount of energy savings, right? Now you can see some images on your screen, some buildings. Yes, I hope there are 5 buildings visible. Yes,
Yes, yes, sir.
perfect. So can anyone tell me, do you think any one of these is energy efficient buildings? Anyone?
So I think third one has blue glasses.
Okay, so you think it is energy efficient, right?
Yes, sir. Those who are getting
Perfect.
sunlight and using the natural light, they are the energy efficient buildings, sir.
Okay. Now, see, again, I want to now change the perspective of this using natural light, right? Uh, uh, Means I beg to differ from this. The reason being, just using natural light in Indian perspective may not be a good option, right? I'll tell you why. Because this concept of having glass windows, right, that came from outside, right, that came from Western countries, which are relatively way cooler, right? They require sunlight not just for lighting purpose, but they also require sunlight for heating. But the problem in our condition, in Indian perspective, is that we are having a lot of sun available with us. We have 40-45 degrees temperature in summers. So it's not just light we are getting in, right? If we compare, since right now I have not added that slide, but if I show you the comparison, right, we take like 10 times more heat if we go with glass instead of a simple what you call wall, right? And that was the basic reason. This is what our ancestors understood, right? And you might have seen that in our houses, not in new houses, but in our old houses, they used to use wooden what you call windows. Yes, wooden windows. When they want air, they will open it. When they don't want air, they'll close it, right? Now the problem with that is very good concept, but when it came to our modern day energy efficient buildings, they talk of only light. They don't talk of energy, right? And light, we can get it from 8 watt bulb, right? But do you think 8 watt would be sufficient for cooling your room? I'm sure no, right? Your AC bill is way more. See, right now, see, in winters, suppose no one is using an AC and no one is using, say, for example, your heaters, right? In India, at least in this Gujarat region, right? So all we do is we are using electricity for our lighting and of course refrigerator and other things. Bills is only 300, 400, maybe 500 per month, right? When you use AC, the bill comes around 3,500 to 5,000, or even more. If you have more ACs, more than 2 or 3 ACs, then it is relatively much higher. So the reason is the cooling, what you call power required, is way more as compared to lighting energy, right? So please think over this this thing, that whether we should go with glass windows or not, right? The only two efficient buildings, as you can see, is towards the leftmost. The first one, it is still under construction. I'm not sure if it is ready. It was scheduled to be started in 2021, but because of the pandemic, this was still under. Last I know, it was still being made. It has shades, and these shades were controlled, right? This building was to be built in Delhi. Same, this one, this is Udyog Bhavan. It is built in Udyog Bhavan. This building, I forgot the name. This one was the first net zero building in India. It is there in Zorbagh in New Delhi, right? The shading, it has used two concepts. It is using the concept of shading, plus it is also the solar panel, so it is generating its own power. So this was the first net zero building that was planned to have built, and this is platinum rated also, right? First net zero building of our country, right? So this is in New Delhi. Then comes now I was talking about, so that is also now this was just how now about increasing the thermal mass of the building, right? If you use a glass, there is a simple glass, so there will be large amount of heat that can come. If we increase the thermal mass of the building, right, we have thicker walls, right? If we have thicker walls, of course the inside would be cooler. This is being implemented in say for example bigger houses, right? Rather we should call it palaces, right? In palaces there are thick walls, right? You go to Taj Mahal and you find it is very cool from inside. Of course we can't build Taj Mahal in our houses, right? Our houses cannot be built like Taj Mahal. So there is an option, right? What we can do is, why not put these phase change materials in between, right, within the walls? And that is what I did during my PhD. How can we build cool houses, right? Of course I tried with a small experiment and it was very successful, so I'll just show it to you. So these phase change materials can form the inner slab, right? Say for example, this is the top surface, this is the inside surface, then in between there can be a single layer of phase change materials like this. What happens, how this phase change material works, that also I will try to show. Say for example, I hope my screen is visible. Is the animation visible?
Yes, sir.
See, light from the sun is coming, right? So what happens is surface is getting heated up, phase change material is also getting heated up, but right now since the temperature has changed to red, now you can see the melting of phase change material has started, but still the temperature over here is constant. Why? Because phase change material has still not melted completely. It is melting, and once it is completely melted, now the inside temperature starts rising, right? Now since up till now, when PCM is actually fully melted, what happens is sun sets. Now sun has set again. Now this PCM is hot, right? Now say for example, again it is at the melting point. Say for example, if melting point is 32 degrees or 35 degrees centigrade, now what will happen? It will lose heat to outside and it will lose heat to inside. Now again, since the temperature of PCM is 35 only, right? So amount of heat, now outside temperature is much lower, right? Plus resistance on this side is lesser. Here you can see thickness is higher, here material thickness is less, so more heat will be lost to the outside, right? And finally the PCM will get cooled during the night time. Again, to provide the same what you call same benefit on the subsequent day, it is important that PCM must regenerate during the night time. Therefore the temperature needs to be set. For US and other places, this research was already done, but they were using PCM for heating purpose, right? They were putting PCM on the outer side, right? And that was their research. No, sorry, they were putting PCM on the inner side of the house, right? When during the daytime it was getting heated up, it was getting charged. During nighttime, it was giving heat to the inside. That is what they did. I thought of applying this in Indian perspective. What I did was I put PCM on the outer side. So what happened? Not exactly outside, just inside. What happened is it takes whole day to melt it, and when it is completely melted, sun goes down, right? So again, it is starting solidifying during the night time, and again it is ready for the next day. So this is how a large amount of heat which was coming, which would have come inside, was not coming, because of which the temperature inside was not elevated, right? So this was some of the initial modeling which I did, putting different PCMs, and then as you can see, I put PCM on the outer side itself, and then I was trying to evaluate. So there was only one PCM that was melting around 34 degrees centigrade, right, which was actually charging and discharging during the night time. So discharging is very, very important because it has to be utilized on the next day, right? So HS34 was selected, but based on the graph, it was rejected. Why? Because there was subcooling, which this was the actual readings that was taken, right? No, this is the simulation reading, and the actual readings I'll show. Now I was talking about subcooling effect. As you can see, if a PCM is, say for example, melting over here, say melting point is around 34 degrees centigrade or 35 degrees centigrade, it is solidifying. When it is solidifying, the solidification starts at 33, but it should have started over here, right? In this case, as you can see, the subcooling effect is only say 1 degree or 2 degrees, right? But in some cases, like for HS34, the reason why I rejected it, the reason was the subcooling effect was some 10 degrees centigrade. This melting started somewhere over here. Sorry, the solidification started somewhere over here. So there was some 10 degrees temperature difference between melting and solidification. This difference in melting and solidification temperature is referred to as subcooling effect, right? Here you can see there is almost an overlap, right? So this material was already good. So that is the reason why I used organic PCMs. Both are organic PCMs. This is ON35 and this is Icosin, right? So these were basically tested, and then I did. So that was the example which I was giving. Now I'll talk about case studies, right? So this was how PCM can be implemented. Then some PCMs I have done the characterization studies, so I'm showing it here, right? This characterization study was carried out using DSC analysis, right? Differential scanning calorimeter. So I was saying that I will be talking about case studies, right? The first case study of utilizing phase change materials is using it for environmental management, right? So I hope you know the person on the screen. Anyone? Anyone?
He's a scientist, but not able to recall his name.
He is the real Funsuk Wangdu.
Yes. It's Bhikhabhai.
He is Sonam Wangchuk, right? So he is Mr. Sonam Wangchuk, and he used the concept of phase change material, and he has changed the entire like community of people living over there, right? There was a problem in Leh Ladakh that people were moving away from their place, right? Because they were not having water, right, during the cultivation time, right? They required water for plantation of trees, for plantation of vegetation in March, right? But glaciers would melt in say June, July, right? And they required water in February and March. So there was no source of water for them because all the water was frozen, So rivers, the water was not sufficient for them. So what happened is a lot of population started moving away from Leh Ladakh. So he came up with the solution of utilizing phase change materials, and and his phase change material was water. Right? He converted it into ice stupas. Right? Ice stupas was, I don't know if you know about it. Right? This was a revolution when it came in 2012. He introduced it in 2012. He started uh, using the water, right, which was flowing unused in the month of November and December. Right? The temperature of Leh Ladakh is minus 15 to minus 20 degrees centigrade, right? Even less during night time. So what he did was he implanted one shower, and what happens is, since water is coming with pressure because it is coming from the mountain, he did it, sprinkled it. Moment it sprinkles, since temperature is well below zero, it solidifies and it falls like snow, and that is what is stored as water. And he has Guinness Book of World Record of storing the biggest amount of snow, right, in natural condition. Right, he was able to store around more than he calls this ice stupa, and the tallest of ice stupa is 64 feet, which he has already built, I think last to last year. Right, it was 64 feet, and it is Guinness Book of World Record of biggest ice structure man-made. Right, and he was able to store 1,50,000 in single stupa. Now you can imagine what happens is, now actual what you call melting of snow will take place in, say, June, July, right? But these ice tuba would melt in February and March, when temperature is around 10 degrees or 15 degrees. This starts melting. So all the water he has stored was actually available for the people during the time of cultivation. And this is how he stopped people from even moving out. So this was a very good environmental solution which he suggested, using water as a phase change material, just storing heat. Just, he was actually not storing heat, I would say he was storing cold. Right, so since it is very cold, so he was storing that cold, and because of that water got frozen, and when water is required, actually it was available during that time in February and March for cultivation and even for drinking. So this was one of the case study which I wanted to show. The second one is, of course, buildings. This one was my work only. So what I did was, I implemented phase change materials within the bricks, right? And I tried to implement it. First, I created these kind of special bricks, right, which was hollow. Then I tested. I made the experimental setup. I tested each brick. Thermal testing was done, and of course there was a weather station which was also available with me. So data of weather station, how much radiation is falling onto the surface, all that, and I just compared. Right, so this was, all the data was taken in the recorder, and it was seen that with phase change materials we were able to reduce the peak temperature maximum by 7 degrees centigrade. Right, just by introduction of phase change materials. You can see this dotted line is for the brick which is without any phase change material, this one. Right, the surface temperature, the inside temperature I am comparing. Right, the inside temperature 2 for this brick is always way higher compared to the inside temperature of others phase change material bricks. So I was able to reduce around 6 to 7 degrees centigrade through this simple experimentation. Right, so you can think of building cool houses just with the implementation of phase change materials. I have not done any other thing except for introducing phase change material. Of course, that was also a challenge, how to build a brick, put it inside and all that. So, and then I also, not just this, I also tried of implementing not a single but double PCM layer brick. Of course, the strength of these kind of bricks was very poor and I was not able to implement it. But then I tested it for testing. Of course, for laboratory still it was possible. So I did it, and I was able to reduce around 10 degrees temperature reduction with the help of two double layer phase change materials. With single layer, I was able to get reduction of 4.5 to 7 degrees centigrade. Overall, for 24-hour cycle, I was able to reduce heat gain by 8 to 12%. I've already told you how heat gain is reduced, right? Because only a portion of heat which is absorbed by phase change material is going inside. Most of the heat is going back uh, from uh, from phase change material back to the environment only. So around 8 to 12% of energy, what you call heat transfer reduction to the inside is being achieved. Now, some of case 33 is basically some of the researches which now we are doing at PDEU. So in that we are utilizing, we are thinking of, like, one of my group is working on utilizing phase change materials for army jawans, right, and even firefighters, right? How it can be utilized for firefighters, because see, even if I can, if my team can increase a firefighter to work for more than, say, 5 minutes more in the extreme condition, then of course that may result in saving quite a few more lives, right? Of course, there are other alternatives are even coming up. Even for, we are also thinking of implementing jackets for army jawans who can, who is standing in sunshine for, say, 50 degrees centigrade temperature or 45 degrees centigrade temperature in Rajasthan. So how can he be feeling comfortable, right? So these kind of jackets we are planning to implement. Then we have also implemented thermal regulation for maintaining temperature, because when you talk about solar drying, right, what happens is, when the crop is actually in the sunshine, the temperature of the crop goes above 60 degrees centigrade. That actually kills the nutrient. So nutrient value of the dried product is significantly reduced. So why not implement phase change materials and reduce the temperature inside the chamber? So that has been implemented, tried and tested. Similarly, one of the research, one of the other MTech scholar has worked on it, is how to utilize phase change material within solar water heating system. Right now, imagine you can take what. See, problem is hot water is available during the daytime. What about night time? Right, actually hot water is required in the early morning when sun has not even come out, right? So why not implement phase change materials over here and then utilize it? So this is what some of my students, they have already done the simulation work, and now we are doing the experimental testing of this kind of system. So for simulation we have done single fin, double fin, multi fin. So this is already under publishing. So I hope it will be out in maybe a week or so. So this is for solar water heating system. Then PCM within heating chamber, so that temperature within the chamber is controlled, right, with phase change materials and without phase change materials. So that has been also tried, and we were able to maintain some 5 degrees lesser temperature, which is also very, very important, because we wanted temperature above 50 degrees centigrade, but it should not go above 60 degrees centigrade, or the nutrition value of the food product is lost. So we have tried, and we are working on this experimental setup, and hopefully we'll be successful. So these are some of the examples where phase change materials are being implemented. One example I've already told you, Sonam Wangchuk ji has already implemented in Leh Ladakh. That is for environment conservation. These are some of the examples where energy conservation is very, very important, right? Otherwise, you might need, like for solar water heating, of course, you if it is solar operated, then it is fine. But otherwise, you are using electricity, and the advantage of electricity is you are getting hot water as and when required. So what if solar water heater can also be utilized to provide hot water during, not just during the day but also during the night? So that is what these phase change materials can be utilized to do so. In the end, I would just like to say, I think time is almost there. So I would like to still say that energy conservation is one of the very, very important, and I'm very thankful to the organizers for organizing this kind of an event where faculties and can be at least told about what energy conservation and what is the grasp of this importance of this energy conservation. I, of course, having my research background in this area, so I have been working in this area for now last say 7 to 8 years, and I try to teach more and more people I meet so that they are also aware. And never think anyone, please don't think that what will happen if I am only switching off the light. What will happen with one light? I have already given you the calculations. If everyone just reduces 1 unit of power, 1 unit of power in one whole year, right, in entire country, right, we will be able to save 1.7 billion units of energy. 1.7 billion units is quite a lot, right? So please think in this perspective. No contribution is small. Even as it has been said, we can even fill oceans, but drop by drop. And this was done drop by drop over say billions of years, and then we have such a big ocean in our on our planet Earth. Similarly, one more important aspect about environment I would like to add, that sustainability must be part of your whatever consumption you are doing, right? It should not be like US, like what they are doing is since now our environment is getting polluted, what we'll do, we'll manufacture things in other countries. They just say that your country will get employment, but what they are doing, they're giving money. You are polluting your environment, right? Your people who are working over there who are getting sick, right? And you are just getting payment. They are just getting meager payment. So that should not be the case, right? They're paying for their health, right? You think the radio which you are getting, maybe you're getting a radio for 500 rupees or 600 rupees, right? But the actual cost of manufacturing can be way more, right? What about the environmental hazards that has been caused during the development, right? So all those things should also be taken care of by the stakeholders, and everyone should be provided proper remuneration. Then only proper sustainability would come into practice. And energy conservation, of course, the topic energy conservation, environment management would surely lead to sustainability. That is the aim, so that our future, what you call, upcoming offsprings are all benefited. This is all from my side. Any questions? Over to the panel, over to the coordinators for the questions.
Is there any participant who want to ask some questions to the sir? Please. Okay, sir. One questions I'm getting.
Yes, sir.
Do you know that is there any current scenario in India where this type of fashion material is being used by common means it's being used for the common people residence purpose?
No, sir. Mine was the first one when I did in 2000. I did my PhD in 2019.
Okay.
So that was the first time, and now we are only working on implementing this. Actually, there has been work on using the thermal mass concept, right? So
Yes.
increasing the thermal mass can be of two types, by increasing the thickness of the wall, right? But the problem is we cannot increase the thickness beyond. Now in Delhi, suppose you are living in Delhi, you are having a 10 by 10 of a house. How can you think of building a wall of 3 feet?
Yes. Yes.
Right. So now this kind of concept is coming up now, since people are not educated enough. They have been only now who are constructing, they are not talking about these all things, right? They only talk of outside beauty. That is why they say make it with glass, right?
Yes.
Which is highly inefficient. Let me
Yes.
tell you, in energy terms, it is highly inefficient of having, means it is actually very good for the builder, right? Because he actually is not building an entire wall. If you see, right,
Yes.
on that entire wall, he's putting a window which is not required,
Yes.
right?
Yes.
So these kind of studies can help in that. So I think you can take this forward, and even I am trying so that educating people so that people can. But yes, I would like to add one thing, that Sonam Wangchuk ji has been working on this. He is building this kind of walls, not with phase change materials, but with other materials. Like he has tried with water-filled bottles within the
Okay.
walls
Okay.
to increase the what you call the energy storage capacity of the wall, and it has been successful. And in fact, one of his project has been approved by government, and he has built houses for the army jawans in Leh Ladakh.
Oh, that's very good, sir. Sir, one question we received from Professor Modi.
Yes.
Which are the most cost-effective PCM?
Again, I would say if you want to go with cost effective, then you should go with inorganic PCMs. Right, these are salt hydrates. Right, many salt hydrates are available. Of course, you have to go with what temperature of phase change material you have to go with, right? Because that is very, very critical, right? So if you are going with a PCM, which is, if you require a PCM for an application of 0 degree centigrade, I would say go with water. It is priceless. It is free of cost, right?
Yes, yes.
And similarly, so asking this question, I would say you should like the most important question is what temperature, sir, right? If sir you are if he's in you just let me know the temperature range so I can let you know which what PCM can be more suitable.
Modi sir, please inform the temperature range for which you are thinking this. I think, sir, he might be thinking for a general living temperature range, like residential building purpose.
So residential building purpose, sir, I think you should go with inorganic PCMs because the cost will be way lesser. Only thing is they have to work on the stability part. So I was not able to get too much stability with inorganic PCM. That is why I went with organic PCM, and the cost is around 600 rupees per 2.5 kg.
Okay, okay, sir. Thank you. And sir, in all over world, is it being used for the common residential purpose?
Yes, yes, yes. It has been used in Spain for a lot. In fact, it has been used in many parts of the world. Only thing is, it has not been used in India because I think their implementation reason was different. Their reason was they wanted to heat their inside environment, right? So they are implementing inside their houses. So that is quite common in European countries, countries like Spain. A lot of research has been done in Spain and England. But for Indian perspective, my research was for building perspective. I did, and there are few more people in my lab who have worked on the same concept.
Thank you, sir. Now, is there any other participant who want to ask question?
I would not say I was the first one. I would just say that more of simulation work was done before. Experimental work was done in quite less in Indian perspective.
Okay. Okay. So I think, thank you, sir. Sir, you actually given very exhaustive data for the first gen material and on the topic of your research work done, which you have carried out in your tenure. And it is very surprising that you have at least built a laboratory model and tried to gather data for different types of conditions, and you have presented it very nicely.
And I would like to add one thing. It is not just model. In fact, based on this, this was also approved by one of the concept. In fact, my supervisor, he has been approved for one full building, and he's developing that building under one project from DST, and he's working the entire building based on this fashion materials and concepts.
It's very nice. That means I think it is being applied at real ground.
Yes, yes. Now it is going on.
That's very nice, sir. So, sir, you have given a very exhaustive data set for this, and I think I'm sure that the persons who is interested in this field will definitely get help from you. So,
Sure.
on behalf of all participants and BN Ministry of Technology and committee members of this STTP, sir, I convey a heartfelt thank you to you for accepting our invitations and giving this such a nice presentations and very informative presentation, sir. We are
Thank you.
happy to hear you once again in future for this purpose, sir. Thank
Sure,
you very
sure,
much,
sure.
sir.
Thank you very much. Thank you everyone for being such a nice audience. Thank you.
Okay. Now, I would request all participants that today's third session is over now, and we will meet again tomorrow morning for the last day, first sessions at 10 o'clock. Thank you.